My name's Lindsay. I introduced myself this morning, but just once again, I'm a grad student right now working with Mike McCoss and Brendan and his team at the University of Washington. We are fairly behind schedule, so what I plan to do in this lecture is move ahead to the parts that I don't think we've covered at all. So the original plan that I had was to go over LCMS parameters such as target list size, the dwell, the acquisition time. Tina kind of touched on some of these, so if you wanted to see it presented a little differently, you can go through the slides at the beginning of this lecture. Then we were going to talk about the components of a liquid chromatography method. If you come from more of a GCMS background, or if you come from like a genomics or a microbiology or a bioinformatics background, that might be a good section for you to familiarize yourself with the LC portion of LCMS. We've already talked a little bit then about retention time and scheduled versus unscheduled methods. So I'll try to skip that and go straight down to predicting retention time with SSRCalc and iRT. So if you have any questions about the slides between the beginning and nearly the end of this presentation, feel free to ask me. But just in the interest of giving you a chance to get some of the hands-on Skyline stuff, I just wanted to present the concept behind SSRCalc and iRT, and then we'll dive straight into using it. So the idea with SSRCalc and iRT, I'm on the slide number 46 in the slide deck if you wanted to follow along. We had this target list in Skyline that includes all of these various peptides for some given protein. We can predict computationally, we just in general as a scientific community can predict very exactly what the MZ, the mass to charge for a precursor will be, just by adding up the amino acids and applying the charge to it. We can calculate MZ for fragments very easily, very accurately, just by adding them up. It turns out we can also predict the retention time for a peptide fairly decently by adding up a hydrophobicity index for each amino acid in a peptide. Some amino acids offer more hydrophobicity to the peptide they belong to. Some amino acids are more hydrophilic, less hydrophobic. If we add up each amino acid component in the peptide, using their retention coefficient, kind of their hydrophobicity ranking, we can get a general idea if a peptide will have an early retention time, a very hydrophilic peptide, or whether it's a very hydrophobic peptide and it'll have a very high retention time. And that's the idea behind SSRCalc, sequence-specific retention calculator. So all it needs is a peptide sequence, some series of amino acids. It'll add up these retention time coefficients and do a little bit of a fancy thing with the N-terminus amino acid. It turns out that one's a little bit special. And then you can get a decent enough ballpark for the retention time for a peptide. To view this in Skyline, you would open up the retention time window in Skyline. You would right-click in the retention time window, and you would have an option like graph, regression, score to run. And you should get a window kind of like this, where you have the measured retention on the vertical axis, and on the horizontal axis, you would get SSRCalc 3.0. And if you're not seeing this or you're lost, totally fine, because we're going to do this hands-on in a minute. SSRCalc 3.0, this is that hydrophobicity index. This is that retention coefficient that SSRCalc added up based on a sequence of a peptide. So you'll see it generally trends. The lower the SSRCalc score, the lower the measured retention time. The higher the SSRCalc score, generally, the higher the measured retention time. So this works decent enough to get a trend, get an idea. But you might already notice that just looking at the points on this graph, it's not fantastic. It's generally a trend, but it's not super fantastic. So this is just what it might look like in Skyline. If you were to click on any of those points, it would show you the chromatogram for that peptide. Each of the points in that window is a different peptide. You can click on it, and it'll bring you straight to that chromatogram. As you start adding more and more targets, it becomes more and more apparent that SSRCalc is maybe not fantastic. You might start seeing a bunch of outliers. Maybe those are things you would want to click on to check that peptide. It's possible that SSRCalc's score was fantastic and Skyline just didn't pick the right peptide. So you might click that and say, well, this had a very high SSRCalc score, but the measured retention time Skyline thought was a low number. So let me look up at the 60-minute mark and check if there's the right peak up at that. At the same time, because we're only ballparking this using SSRCalc, because we're only using the peptide, the amino acids retention coefficient, we could do better. And doing better would be doing something empirically. And the empirical method is called iRT. iRT stands for indexed retention time. And the idea behind iRT is that we will use anchor points that are peptide standards that we know elute very early, sometime in the middle, and very late. And we'll just put those like stakes down in the retention time space, and all of our peptides that we're interested in for our experiment will fall somewhere along that line. So if you imagine a football field, we have like the mid and then the two end points. So if we measured goal to goal on a football field, no matter what football you're talking about, it's going to work for an analogy. And we measured 10 equidistant points across the field. If I told you go to point 10, it doesn't matter if I'm talking about American football or if I'm talking about European football, you would go to wherever the end of the field was, right? So it's similar with indexed retention time. Doesn't matter if you're talking about a 90-minute gradient, a 60-minute gradient, a 5-minute gradient. If you have those stakes down in your sample, you have the index retention time standards in your sample, you know that going to the end is going to 5, or going to the end is going to 60, because it's just the end. So that's exactly what we're doing in LCMS space. Instead of a football field, we're talking about retention time. So if I put down retention time peptide 1 is a standard, and I know its sequence, and I know it elutes at 5. And I know that peptide 2, my second standard, elutes at 25. I know peptide X is somewhere in the middle. If I have those same standards in a new sample, and I know that peptide X is somewhere between standard 1 and standard 2, it doesn't matter what the new gradient is, if it's a long or a short gradient, if the sample is being run on a different mass spectrometer system. I know I can look in between those. So now peptide 1 is not eluting at 5. The standard is eluting at 10. And peptide 2 is not eluting at 25. It's eluting at 50. So I can kind of guess, well, if I know it's going to be halfway in between, I can look for peptide X halfway in between my two standards. So we can see this in Skyline again, going to the right click in the retention time panes and the regression. And we can change the calculator, and we'll do this all hands-on, to instead of SSRCalc, we can change it to iRT if we have this set up. And in the tutorial, we're going to set that up. You can see already that these standards, the relationship between the iRT score, which is empirically derived, and the measured retention time is a lot more accurate. It's a lot more precise than it was with SSRCalc, which was just kind of a general rule of thumb. Just to remind you again, SSRCalc looks something like this. iRT looks something like this. The regression is a lot better. If you don't want to use iRT, it's fine, as long as you're okay with it being not quite as precise. Just showing you the same thing again. Any questions about the difference between SSRCalc and iRT, or just the general concept of iRT? A little bit intuitive? So we're going to be setting up one of these calculators in just a bit, but I wanted to talk really quickly about choosing what those iRT standards are going to be. There's kind of generally two options. One is you can buy an exogenous commercial standard that you would spike in, and the other is you can pick some set of experiment-specific peptides that are always in your sample. Differences between these, it's really nice to use the commercial kits because they're extremely reliable. They're like QC'd, they're always the same, they're usually heavy labeled and like very pure. However, they're kind of expensive depending on your lab's spending. So it's extremely cheap and basically free to use peptides that are present in your sample because they're always present in your sample anyway. The flip side of that is that they must be present in every sample if you're using endogenous peptides. So if I want to use some protein from yeast, I'm doing a yeast cell lysate type of experiment, I better make sure that protein is in every single yeast sample that I prepare. If it's not, I'm missing one of my anchors and my calculator would be broken. There's kits from a ton of vendors. There's kits from Pure, Sigma, Biognosis. We'll be using the Biognosis one in our example data, but it's not specific necessarily to Biognosis. Common endogenous standards that I've seen people use are like keratin because it's in all of your samples anyway. I've seen albumin because that's, if you're doing anything like non-depleted plasma, that's typically in everything too. Again, you just have to make sure that if you are going to use something like keratin, it is actually in all of your sample, which is kind of weird to wish for. And one of the reasons you might want to use this, if you're thinking like, oh, that kind of sounds like a lot of extra work, I just optimized my CE, I did all these extra steps to build prior knowledge. This is showing you the view in Skyline for this same type of sample over time on a column. And then this last point, this last sample, I switched to a new column. My last column got clogged. Over time, my retention times for this single peptide, they started at about 26 minutes, and then over time, they drifted all the way down to almost 18 minutes. So that's like a pretty significant retention time drift. But then notice as soon as I put a new column on, it pops right back up to like 28-ish maybe. So every time you change a column, your retention times will shift just a little bit because they're probably not going to be exactly the same. And then just over time, as your column ages, retention times tend to get earlier and earlier. So knowing with those peptide standards, those iRT standards, if your peptide's going to be eluting earlier and earlier versus later can be really valuable knowledge. So not even if you're specifically scheduling a method and you need to know your retention time windows to do a scheduled targeted method, it's even helpful if you're doing unscheduled methods to be able to pick those peaks and know where to look for them. So that was kind of like very quickly the entire lecture. We're going to jump into the tutorial now. But the main points, peptide retention time has nothing to do with your mass spectrometer. It is entirely that instrument that we often ignore that's in front of your mass spectrometer, the liquid chromatography system. SSRCalc is nice because it only requires the peptide sequence, doesn't require any other information. iRT is better than SSRCalc if you can set up those calculators and those standards, which we're doing next. Skyline supports both. So you can always start with SSRCalc, build your iRT, and then use iRT down the road. I've got a ton of additional information if you found this fascinating. And now we're going to jump into Skyline. So you should have an iRT 2019 folder